Welcome back. In this segment, we're going to be studying the beginning and easiest parts of elementary probability theory. Now, I'm not going to keep it so easy. I don't want you to be bored with too much easy material, but we're going to have the beginning stuff and how we use this to further our statistical studies and further make inferences later on when we get to the higher level chapters. Well, many people know, in fact almost everybody knows, that if you toss a coin, you have a 50% chance of getting heads, 50% chance of getting tails. Now, what most people don't know is the reason is not because there are two sides to the coin. Most people think, well, there's two sides, and so there's an equally likely chance of getting heads as tails. Actually, even though there are two sides, it could be that a coin is weighted more one way than the other way. Several people, including Susan Dean, a professor of mathematics at De Anza, who is my partner with this course, she has tossed a coin over 4,000 times and counted the number of heads that she got on that. Well, so what she did was she counted the number of heads, and she saw that this number approached 2,000 out of the 4,000 times. And so using a long-term relative frequency, she predicted that the probability was approximately 50%. Now, if you toss a coin 4 times, you would not be surprised, most likely, if you ended up with 1 or 2 or 3 heads, which varies far from 50%. But as our number of times of doing an experiment gets larger and larger, we do expect the empirical probability, which means what do we get from doing our experiment, to approach the theoretical probability, which is in theory what do we expect to happen. Very often there are articles in the newspaper that deal with probability. For example, very recently I read an article in the San Jose Mercury News, and this was a study, an epidemiology study on the probability of getting hepatitis C and whether it was more likely or the same or less likely to get it if you've had a tattoo at a commercial tattoo parlor versus if you haven't. And in this particular article, the study was done on 626 patients, and it found that if the patient had a tattoo, the probability that the person had hepatitis C was 1/3, meaning 1/3 of those people studied who had tattoos and had them from a commercial parlor had hepatitis C. But if you didn't have a tattoo, then the probability of having hepatitis C was 3.5% as opposed to 33%. So this involves probability and using probability to then make decisions or suggestions about how we should proceed. Another case involving probability theory, which was from a book that I found fascinating, was a book written by Gary Kinder called Ship of Gold. And in this book, he talks about trying to find a ship that went down during the California gold rush off the East Coast. It went down in a hurricane, and how he didn't use these words, but explained how he used the mathematics of probability theory that was developed during World War II for the United States to detect the German submarines, and how he used this probability theory to detect where the ship might actually be. And amazingly, which is why there's a book out by it, amazingly, Tommy Thompson, who was the engineer, Gary Kinder's the author of the book, Tommy Thompson, who was the engineer, was able to find the ship beneath the ocean, this huge ocean, zero in and find one ship. All right, and these are just 2 examples. Almost every day in the newspaper there's another example that involves probability theory. So we're going to start with a really boring example because this is an easy way to learn the material. And then as we proceed, you'll go a little bit further in being able to use this towards more complicated cases. So right now what I have up here is I have a case where we have 4 red cards and 9 green cards. And what our experiment is going to be is to randomly draw 1 card from this. So we're going to pick 1 card out of the 13 cards here. And I'm going to record some events. R is that the event that the card was red, that was picked. G is that the card is green. And even is that the card was, E is that the event that the card was even. So we have R if the card was red, G for green, and E for even. And we're only picking one card. Our sample space is the list of all possible outcomes that we could possibly have. So in this case, our sample space would be a red, the first red, the second red, the third red, or the fourth red. And I just numbered them 1, 2, 3, 4. And that's how I can deal with the evens and the odds. And the greens, 1, 2, 3, 4, 5, 6, 7, 8, 9. So each card is either red or green, and it has a number on it, from 1 to 4 or for the reds, and 1 to 9 for the greens. Now, each outcome is equally likely. That means the probability that we pick a red with a 1 on it, there are 13 cards, would be 1 out of 13. The probability that we pick a green with an 8 on it, again, there are 13 cards, so it would be 1 out of 13 again. Now let's go to the events. Event R is picking a card that is red. So in this case, we could pick R1, R2, R3, or R4. Those would be the red cards. The probability of picking a red card then, there were 4 red cards out of 13 cards. So the probability of getting a red card would be 4 out of 13. The probability of getting a green card is asked for next. Well, event green would be G1, G2, G3, up to G9. The probability of getting a green, there are 9 green cards out of 13 cards. All right, let's go on to the next one, E. That's a little bit different. That means we're going to look at our sample space and pick the cards that have an even number on them. So we'll have R2, R4, G2, G4, G6, and G8. And so our set in this case would consist of those cards, R2, R4, G2, G4, G6, G8. And if I count them up, I have 1, 2, 3, 4, 5, 6. And so the probability of picking a card that's even would be 6 out of 13. That's the probability of getting an even card. All right, we have a little bit more to do, and then a lot more, actually. And now what we're going to look at is what is the complement of G. And this does not mean, oh, set G, you are so lovely. In fact, what it means is not or opposite. The complement of G is G prime. It means not G. So if the probability of getting a green is 13, the probability of getting not green is the same as the chance of getting everything else. We go back to the not greens, and there were 9 greens, and there are 4 not greens. If we add the probability of green plus the probability of not green together, we will get 1. And this is always the case. If we add the probability of an event plus the probability of not having the event, we add those together, we will always get 1, or 100%. All right, now I'm going to go on to some more of these right here. Getting a little bit more difficult, but you can handle this. All right, let's look at this one now. The probability, we're going again to just pick one card, and the probability that the card is red, knowing that it was even. Well, in this case, we're not looking at all the cards that we have. What we're looking at is the cards that were even. So remember, we had 13 cards. Out of those 13 cards, 6 of them were even cards. So we're going to reduce our sample space just to those 6 even cards. And out of the 6 even cards, R2 and R4 were red. So we had a probability of 2 out of 6. I want to just go over this one once more to make sure everybody has it. We first reduced our sample space to just the even cards. Out of the even cards, 2 of them were red. So the probability of red given even is 2 out of those 6. The next one, the probability of red and even. This means we start from the very beginning again, and we're going to look at picking one card, and there are 13 cards to choose from. And out of those 13, how many of them are both red and even at the same time? Well, the reds are R1, R2, R3, R4. The evens are R2, R4, G2, G4, G6, G8. The ones that are in both cases, red and even, are the R2 and R4. So there are 2 of those. 2 out of the 13 cards total fall into both cases. Going along now, what OR means, OR is sort of special in mathematics talk. OR means one or the other or both. So if a card is red or even, it means it could be red, it could be even, or it could be both red and even. So it could be just red, could be just even, or could be red and even at the same time. So we add up all our reds. We had 4 reds. We had 6 evens. But now, what hopefully you notice is when we had 4 reds, we had red 1, red 2, red 3, red 4. When we had evens, we had red 2, red 4, G2, G4, G6, G8. 2 of those cards were counted twice. The red 2 and the red 4 were counted twice. So we have to subtract out the cards that we counted twice. In fact, it's these 2. So we have the probability of red plus the probability of even. And now we're going to subtract out the overlap. And so we have 4 plus 6 is 10, minus 2 is 8 out of 13. In just a minute or two, I'm going to summarize these rules so you'll have them all together as they are in your text. The next topics are mutually exclusive. Mutually exclusive means that one excludes the possibility of another one happening. Now, several years ago, I read in one of the local papers a survey. In fact, this was a face-to-face survey, and some people were interviewed, and their picture was then recorded in the paper with their caption. And the question was, where do you go for nightlife in Cupertino? And the person, who I'll just sort of assume must have been a Math 10 student, the person said, nightlife and Cupertino are mutually exclusive events. So what that means is, if he's in Cupertino, there would be no nightlife. And if he wants to have nightlife, he doesn't come to Cupertino. So let's go back to this example. Red and even, are they mutually exclusive? Well, could a card be both red and even at the same time? And as a matter of fact, we saw yes, there were 2 cards. So the answer to this would be no. No, they are not mutually exclusive. Now the reason is because the probability of red and even equals 2/13. If they were mutually exclusive, they couldn't both happen at the same time. So the probability that they would happen at the same time would be 0. So if they're mutually exclusive, the probability of both happening at the same time would have to be 0. Because the probability is not 0, then they're not mutually exclusive. Let's try this one. Red and green. Are events red and green mutually exclusive? This means, could a card be both red and green at the same time? And let's think about it. The cards only have one color on them. So a card cannot be both red and green at the same time. So in this case, we would say yes. They are mutually exclusive. And the reason is that the probability of red and green equals 0. a card cannot be both red and green at the same time. So just to recap that a little bit before I go on, if two events are mutually exclusive, they both can't happen at the same time. And so how you find out, one way, if they are mutually exclusive, is you find the probability of both occurring at the same time. If the probability is 0, that means they're mutually exclusive. If the probability is not 0, that means there's some overlap and they can both occur at the same time. If the probability is 0, they are mutually exclusive events. And if the probability is not 0, then they are not mutually exclusive events. All right, one last concept before I go on with a summary. Independent. If two events are independent, that means that one happening will not affect the probability of the other happening. So knowing that the first one has occurred does not affect the chance that the second one occurs. So let's look at these two, red and even. In general, the probability of red was equal to 4 out of 13. The probability of red, if the card was even, though, is equal to 2 out of 6. So now what we have to decide is, are these two the same? Meaning, if we were to put this in decimal format, would 4/13 be the same as 2/6? And the answer is no, they are not the same. So what that means is this extra information of knowing that a card was even affected the probability that a red be picked. So in general, out of all cards, there was a 4/13 chance of picking a red. Now, if we look at just the even cards, so first we reduce our sample space to the even. Now there are only 6 even cards, and there's a 2 out of 6 chance of getting red. Because this probability changed with the extra information, we would say that R and E are not independent events. All right, now let's look at R and G. Are events R and G independent events? Well, the probability of a card being red is equal to 4 out of 13. Knowing that the card was in fact green, so in this case, we're saying that the probability that the card is red is 4 out of 13. But if we're told, by the way, the card I picked was green, now what's the chance that it's red? That would be 0, because these two are mutually exclusive. Making that the card was green excludes the probability that it's red. So it changes the probability, and the probability of the card being green now is 0. I'm sorry, the probability of the card being red now is 0, and so we would say these are dependent events. They are not independent events. All right, so as a summary now, let me put up the summary of these rules. The first rule that we're going to have is the basic probability rule. The basic probability rules, actually they're both called the basic probability rules. The first one we're going to have is the multiplication rule. And the multiplication rule says if we wanted to find the probability of A and B happening, we find the probability of A times the probability of B given A. Or we could do this the other way. The probability of A and B is the probability of B times the probability of A given B. So this is our multiplication rule. Another way we can write this is we can divide both sides. Here, I'm dividing both sides by the probability of B, and so I can find my conditional probability by knowing what the probability of both occurring at the same time is and dividing by the probability of B. Let's go on. If A and B are independent events, then this extra information of knowing that B happened does not change the chance that A happens. So this is how we can test for independence, is if the probability of A occurring is the same as the probability of A occurring knowing that B already has occurred, if these are the same, then B did not have any effect at all on A. If they are equal, then they would be dependent events. This also means that the probability of A and B can be rewritten as the probability of A times the probability of B only when A and B are independent events. All right, the next rule that we have is the addition rule. And we saw this one with the cards also. The probability of A or B is the probability of A occurring plus the probability of B occurring. And now you need to subtract out what's been double counted. We just saw this with the red or green. We had to subtract out those two cards that were double counted. So the addition rule says if we want to find the probability that one or the other or both happens, that means find the probability that the first one happened, add the probability the second one happened, and count it out, the double counting. So what would happen now if A and B are mutually exclusive? If A and B are mutually exclusive, the probability of A and B both happening is 0. So this 0 would go in place here if A and B are mutually exclusive events. So mutually exclusive events mean that A and B have no common members if we're counting membership, or they can't both happen at the same time. Sometimes we're counting membership, meaning red card and green cards. Other times we're dealing with situations that don't have members. For example, if you want to find the probability that it's completely sunny outside and at the same time that there's a huge thunderstorm, we're not talking about members. We're talking about two events that are occurring. I'm going to do one example. Actually, you can do the example that is in the textbook with Carlos playing college soccer. That would be a good one, because what I'm going to do next is the contingency tables. And the contingency tables provide a way of displaying probabilities and frequencies, and it's also an easy way of determining conditional probability. So what I took here is I have the data from the end of the year 2000, and this was data that was published and a summary that was published by the Santa Clara County Public Health Department. And this was their annual AIDS surveillance report, meaning it went through December 31st, 2000. And they included information on the cumulative number of cases of AIDS that have been reported in the county, and they broke it down by age, by ethnicity, by risk factors. And in total, there were 3,058 adults by the end of December 31st, 2000, who had reported cases of AIDS. And so what I'm going to do is I'm going to put up this chart. This chart is similar to one that's in your textbook, although the textbook has a previous quarter's data. And on this chart, you can follow with the homework and just to see the headings. We have it broken down by gender, female and male. And then what I broke down was the risk factor. Now, this used to be called homosexual bisexual activity, and then in this latest report I noticed they changed this to MSM, which is men who are having sex with men. IV drug users, and I've included the MSM group with that. People whose risk factor was heterosexual contact, meaning with somebody who had AIDS, and all the others together here. And so this is a table. This means that there were 0 females who ended up with their risk factor of being a male and having sex with a male. Well, that part makes sense. But there were 73 females who were IV drug users, 140 who contracted the disease through heterosexual contact, and so on. And you can read this. Now, by hand, what I've written up are the summaries. Adding across 0 plus 73 plus 140 plus 58, we get 271. Adding down, we get here 2,201. And the total number of adults was 3,058. I didn't include the children in this case. Suppose that one person from the county with AIDS is randomly chosen. The probability that that person is male. So what we do is we look at all the males. There were 2,787 males going all the way across out of a total of 3,058. So our answer would be 2,787 divided by 3,058. The probability that the person has a risk factor of an IV drug user. Well, now we will go down and we'll have 549 out of 3,058. And I'll just do two more here. So 549 out of 3,058. And if we go down and do one more, let's say the person is male or has a risk factor of having sex with men. So the person is male, that's 2,787 out of 3,058. Or the risk factor is the risk factor is men's sex with men, 2,201. Well, now what's happened is we've double counted, so we need to subtract out. Let me do one last one. How about the probability the person is male, given that the risk factor was other? In this one, we're looking at the other column. We're not looking at all 3,058. We're going to reduce just to the 108 others. See, just to the 108 others. And out of the 108 others, we have 50 that were male. So as you can see, one of the advantages of this chart is it's easy to summarize the data and to go from here to find the fractions and then use your calculator. Well, that's the brief overview of elementary probability using the probability rules and contingency rules. Now it's your turn to go home, read the text, and work out some problems. And I'll be back.